Hello, everyone. We're just working on Grady's slide sharing there for you. We're just going to try and get him back. But in the meantime, there is a session, as I've just mentioned, talking about a reaction to the Social Dilemma Netflix documentary, which has proved to be very thought-provoking at this time. The team at Inspired Minds have assembled an expert crew of people to discuss it. That is happening right now on the session stage. And also, as I've mentioned, on the KPMG cyberspace, we have Zhao Bin from Huawei, who's about to start on AI Insight Talks. Grady, welcome back.
Thank you. Are you able to see my slides now?
We're just going to confirm that it will start sharing. So if you want to just share your slides, and then once that's going.
In theory, I did. Let's see. Oh, here we go. Let's
Fabulous.
this now.
Let's have a look.
Oh my God.
Don't worry.
Computers.
We've got this.
Computers can't live with them and can't live without them. All right.
There you are. You're
Let's
good
give
to
this
go.
a shot then. Oh, and you're seeing the wrong slide now. Let's move this over. Holy cow. Okay.
Don't worry.
My
all
gosh.
is well.
If only I understood computers. All right. You can see my slides now. Let's give this a shot. Phew. Okay. I work at the intersection of computing and AI and software architecture. So let's get a few definitions out of our way. To begin with, what I mean by AI is simply a system that reasons and that learns. Anything else, and it's not AI. From the perspective of software architecture, I've got a fairly simple operational definition. All architecture is design, but not all design is architecture. Architecture represents significant design decisions that shape the form and function of a system, where I measure significant by cost of change. Now, truly, we can view this as an engineering problem because, as in all engineering disciplines, we're trying to come up with reasonably optimal solutions that balance the forces upon that system. In software-intensive systems, and AI is a software-intensive system, we're attending to these kinds of forces that weigh upon us. Your mileage varies because different domains, different cultures, different complexities, these all change the dynamics of what kinds of forces I have. One of the other lessons we have in software architecture is that there are multiple views by which we look at a system as relevant to the particular concerns of groups of stakeholders. This is an idea made manifest in the work of Philippe Kruchten in his classic IEEE paper, the 4+1 view model, and has been codified in the ISO IEEE standard 42010, I believe it's called, on architectural description. Now, if you look at the architecture of a typical web-centric system at scale, you get something that looks like this. And this is a whole lecture unto itself, so I'm not going to spend my time there, but you can think of architecture as representing, in this case, the deployment view, the physical components of a system and how they connect with one another. If we look at it from the perspective of microservices, this is what you begin to look at. This represents the specific APIs and the calls between them in both Amazon and Netflix. It's clear that these are systems of extraordinary complexity. Now, again, your mileage varies, but this is not atypical of a web-centric system at scale. But not all software systems are these kinds of systems. If you look across the entire range of software systems, you'll see that there are indeed many different styles, many different domains in which those styles apply. But one other thing we find consistent within them is that all such well-structured systems are full of patterns. Now, what do I mean by a pattern? There's the classic book Design Patterns by the Gang of Four, which codified this, at least in the world of Smalltalk and in the world of certain classes of languages. But what is obvious is that, or what's fairly clear from experience, is that these kinds of patterns appear no matter what domain and no matter what language you're working in. The civil architect, Christopher Alexander, expressed these ideas greatly in his series of books, the most classic of which is A Pattern Language and the Timeless Way of Building. Herbert Simon in The Sciences of the Artificial discusses this in some detail as well. Mary Shaw and David Garland in their book, Software Architecture, cleverly titled, attempted to codify the main kinds of design patterns they found architectural patterns they found within systems, things such as blackboards, pipeline architectures, object-oriented kinds of architectures, and the like. And what we've begun to see is the emergence of these kinds of architectural patterns for classic symbolic systems. And you'll see a few of them here, but you can roughly organize these kinds of patterns into various categories. But notice I used a very important word there. I said symbolic systems, because most AI systems these days, especially for deep learning, are neural in their nature. What is happening in this world, in the world of AI, is that we're beginning to see the emergence of these kinds of architectural patterns because this represents a maturation of the community. As one example, we've been trying to do this with the Robonaut 2. Just to clarify, it's the beast on the left side of this picture. Robonaut 2 is an interesting one because this particular one was actually up on the space station for a while. It's been brought down for some repairs, but it represents a really interesting set of use cases. In fact, this is one that's inspired most of my work the last several years in AI. So consider the mission to Mars. It has two very interesting characteristics associated with it. On the one hand, it has the problem that given the speed of light issues, you can't rely upon mission control on the ground. You have to literally take mission control with you in the skin of the Orion spacecraft. And so this is the HAL problem, the HAL scenario, but as was mentioned at the beginning, minus the homicidal features. Additionally, NASA wanted to put robots on the surface of Mars before the humans arrived in order to prepare the site, build structures, and later on act as companions and assistants to the astronauts themselves. So, given the work we at IBM had been doing with the Johnson Space Center and other kinds of things in the area of what we would call embodied cognition, we viewed this as an opportunity to see if we could build a system that would attend to those particular use cases. So literally one afternoon, I sat down and said, I think I know how to architect this. And indeed, architecture was the key of what led us forward. We've been able to apply what I built, and we'll talk about it more here in a moment, to not just the Robonaut 2, but also to a variety of other robots. Sophia, we spent some time with. We put it behind some ABB robots, and even avatars such as found within Soul Machines, and even robots such as Pepper and Now. So let's go down this path, because although we have the book Design Patterns in the symbolic case, no one has yet written such a book for the neural world. Perhaps it's one of you who might do so. Let's take a look at one architecture. It is the case that even neural systems, even AI systems, have architectures. Indeed, it's fair to say that every software-intensive system has an architecture. Some of them are accidental, some of them are intentional. Most of them are born from the decisions made over the lifetime of its implementation. My wife's a child and family therapist, so when I go in and work with a project, one of the first things I'll do is to apply a technique she uses in family therapy. Draw me a picture. So I'll sit down with the architects and have them draw me a picture of the architecture of their system. This is the architecture of Watson for the Jeopardy challenge. Now, this may not make a lot of sense, so let's translate it in the form of some UML. This is actually a little bit of a loose form of UML. Watson Jeopardy is a pipeline architecture. So even now, we can begin to classify it as a classic architecture. You get a question set at the beginning. This is during operation, not training. We take that, we run it through a pipeline in which we break apart that question and we do an analysis on it, which actually generates several thousand possibilities. We then do a search on that, sort of forward chaining here, in which we then generate several tens of thousands of possibilities. And then we do a reverse chaining and apply to each one of those tens of thousands potential evidence that supports it. And now we're dealing with potentially hundreds of thousands of different entities going across here. And then we score it. And all this happens, thanks to the massive amounts of hardware we threw at it, within just a few milliseconds. That's the architecture of Watson in a nutshell. Now, other systems, AI systems, seem to have architectures that are emerging as well. AlphaGo is one such good example. So there are a few papers that have been written about it. We begin to understand the structure that they have. So it's a fairly classic layering of neural networks, although they do some very clever things in between some of those layers. What's happened also is that the AlphaGo work has been matured into AlphaZero. And thus, we have another lesson for the maturation of architectures. As is with symbolic systems, what you tend to find is that these kinds of architectures start small, but then in use, as Parnas observes, will tend to grow and stabilize those design decisions until you have a reasonably well-structured set of design decisions and their patterns that can be applied to a large set of domains. This is true very much of AlphaGo to AlphaZero in its journey. The same thing is happening in the world of GPT-3. So, well, it's version 3. We've seen previous versions before it. And looking at it from the outside, you can also see that its architecture has evolved over time. GPT-3 is basically a transformer architecture. And the very fact that I can name that architecture, again, is a representation that we have the codification, or the beginning of the codification of the naming of different kinds of architectures that exist for us. So again, GPT-3 has not been exactly forthcoming with describing the details of their architecture, but knowing that it's a transformer, we can begin to infer some of the ideas of the design decisions they have made. Another lesson we can learn from this, as looking at both Jeopardy and GPT-3 and the AlphaZero work, is that architectures tend to evolve to a place where you begin to produce ecosystems around them. So it's not just the architecture in terms of the software side, but it's all the other pieces around it. The APIs, the tools, the training materials, and the like. All good architectures tend to evolve that way. We're involved in, as I mentioned, this architecture around the system for the mission to Mars. And this is the beginnings of an architecture for it. So this is UML again. And yes, indeed, one can apply traditional kinds of modeling techniques even to AI-based systems. And what we're expressing here is, in Philippe Krushton's terms, the logical view of this architecture, in which we describe the vocabulary of the solution space. And in that vocabulary, we're basically describing the main abstractions that exist. And if you look closely, you'll see you've got things like agents and blackboards. Yes, indeed, this is an agent-based system. Now, as I said at the very beginning, architecture represents a set of significant design decisions. And I want to expose this a little bit because this is a great example of how one expresses those decisions. Self, and we name it that because it's a rather introspective system, is guided by these 6 major design decisions. First, we say that behavior emerges from a constellation of mindless agents. This is Minsky's society of mind. Second, we make the assumption that knowledge is incomplete, contradictory, multimodal, sometimes intractable, and often wrong. This is Brooks' idea to a degree of intelligence without representation, and it leads us to his subsumption architecture. Again, a codification of an architectural pattern for AI. Gary Marcus has brought us the ideas of innateness, and these are also an important design decision, assuming that in self, we have a system with a small set of inherent concepts. Yes, we could sort of learn everything, but I choose not to spend several million years of computation time to evolve that. We also throw in the ideas of Hofstadter's Strain's loops, the idea that a system can know itself, and the system itself is a first-class citizen of itself. This brings to mind some of the ideas of Smalltalk and its meta model architecture. The last 2 elements are part of software engineering. Another factor we're finding in AI systems is, yeah, we see some really nice things in the laboratory, but frankly, if you want to bring these things to the real world and make them industrial strength, you've got to worry about issues beyond just the algorithms within them. So, for example, we have a clear separation of concerns between the logical and physical elements of the system. You saw earlier the diagram, and I'll bring it up, of the logical elements, but actually these manifest ourselves in our system as a set of Kubernetes containers. Oh my gosh, we're talking about using Kubernetes in the context of AI. Seems strange, but in the world of hybrid symbolic neural systems, it's seems to be very much the future. And indeed, it leads us to the last decision. If you're trying to build a system that's not just a one-shot thing that runs on your smartphone as a client by itself, but rather potentially has millions of simultaneous users across the globe, then you've got to worry about a computational fabric that's unreliable, insecure, and scales. This is where AI meets software engineering. There are a number of cognitive architectures that have emerged over time. Things such as ATCR from CMU, SOAR, a rules-based architecture, HTM coming from the good folks of Numenta, DeepMind and OpenAI I've alluded to, and the self architecture itself. So these are all interesting things. So here's where I'll last leave you. We're in an interesting place in the world of AI because we're seeing the intersection of symbolic systems and neural systems. And because we want to bring these things out of the laboratory into the marketplace, it means that all of these issues apply to us. We've got to deal with, you can't violate the laws of physics. Information you can't pass faster than the speed of light. A lot of the concerns we face here, therefore, are in the area of architecture and the organization that builds that architecture itself. I'll wrap it up here and say that, hey, don't forget that every time I gain a Twitter follower, an angel gets its wings. So here's how you can reach me. I'm eminently accessible. Feel free to reach out and drop me a line if you'd like to. Thanks very much. And wow, we got it done, but you didn't see me, and I promise that I'm not a bot, but it really was Grady. Thank you.
Grady, thank you so much. That was so fascinating. And you're sticking around for some questions. So if you'd like to join Grady and ask him some questions, you can click on the Networking Lounge for the speaker Q&A room. The link is going to be dropped now into the session chat, and then you'll be able to ask questions. And Grady, hopefully if your camera is able to come back on, otherwise we'll stick to the answering questions.
Sounds good.
Fabulous. Thank you so much. And everyone else, will be back after a quick break. If you haven't yet, do try some one-to-one networking via the networking tab, and we'll see you after this very short break.